This is video 23 in the lectures on the design of reinforced concrete beams. This lecture deals with minimum reinforcement and crack width calculations. The minimum reinforcement is governed by two principles. You have minimum reinforcement for crack control, and you have minimum reinforcement for brittle failure or to avoid brittle failure. Let's start with minimum reinforcement for crack control. When the tensile stress in the concrete is exceeded, the minimum reinforcement should cover this. So that means that the tensile force in the reinforcement must be equal to the tensile force in the concrete, or the tensile force capacity of the concrete. It means that the total force FTS must be equal to FTC. The total force in the reinforcement is simple. It's the area of the reinforcement multiplied by the stress. And for the concrete, it's the concrete section in tension times the effective concrete stress multiplied by a factor taking into account the stress distribution. It can be a rectangular or trapezium form, and a scale factor. If now AS is set equal to AS min, then we got this formula for the minimum reinforcement for crack control. AS min is the minimum reinforcement in the tension zone. Now, if we analyze this formula, we have here sigma S, and sigma S can be taken equal to FAK or to a lesser value which corresponds to a crack width limitation. So if there is no specific crack width limitation, then sigma S is taken equal to FAK, otherwise it will be limited. The factor Kc is 1 for tension and it's 0.4 for bending. The scale factor K is the scale factor corresponding to the depth of the beam. And FCTF we can take as effective tensile stress, the mean tensile stress of the concrete, which is given by the formulas given here. And ACT is the concrete area which is calculated to be in tension just before formation of the first crack. So that means that for bending, it's half of the section of a rectangular section, and for pure tension, it's of course the whole section B times H. Now, if we look at this formula and we make a little graph with on the x-axis the total depth of the beam, and on the y-axis the reinforcement as a percentage of the cross section. And we do that for different concrete grades. Then you will see that if your concrete grade goes up, then the minimum required reinforcement as a percentage of the cross section goes up too. So this means that on site, when the reinforcements is already there and you are going to concrete, to pour the concrete, then don't pour concrete which is stronger than the required concrete. If you do that, the minimum reinforcement will not be sufficient. So take care of that. When the total depth of the beam increases, then the minimum reinforcement decreases. Now we look at brittle failure, the minimum reinforcement needed for brittle failure. That means that to avoid brittle failure, the beam must be reinforced for the cracking moment. And the cracking moment, it means that the cracking must be equal to the moment that can be taken by the reinforcement. The cracking moment in its easiest form, pure elastic, is FCTM times BH squared divided by 6. And the bending moment that can be taken up by the reinforcement is just the reinforcement times its stress times the lever arm. And if you rearrange it, and then we assume that the effective depth is more or less 0.9 the total depth, and the lever arm is more or less 0.8 times the effective depth, and you fill this in this formula, then you arrive at a formula saying that the minimum reinforcement is 0.26 FCTM divided by FAK times BD. So brittle failure, we have seen that this is the formula for brittle failure, or to avoid brittle failure. There is also a limit to it. It must always be bigger than 0.13% of BD. Now for bending, when the steel stress equals FAK, then the formula for brittle failure is always dominant. So when brittle failure is not expected, then the minimum reinforcement can be taken as 1.2 times the calculated reinforcement in ULS. When the reinforcement put in place is less than the minimum reinforcement, then you must consider the element as plain concrete and not reinforced concrete. And the maximum reinforcement is also a maximum reinforcement in tension and compression is 4% of the cross section. When you want to limit the crack width at your minimum reinforcement, then you can do so by limiting the steel stress not to FAK but to a lower value. And this lower value is given by this table in the Eurocode, and for each obtained crack width it gives you a maximum bar diameter, and a maximum steel stress. So for a bar diameter of 10, the maximum steel stress is 320 megapascal for a crack width of 0.3 millimeters. So you can do the same calculations, but you calculate sigma s coming from this table. Now, this table is only valid when the concrete cover is 25 millimeters. We know already that in most cases the concrete cover is more than 25 millimeters. This table is only valid if the effective or the mean tensile stress in the concrete is 2.9. That means that's only valid for a concrete grade C3037. It's only valid for bending. For pure bending, the D must be equal to 0.98. The K1 factor must be high bond bars. The form factor is 1. It means that the total depth is smaller than 300 millimeters. This is most likely not the case for a beam. It's more likely that this is for slabs. The table is only valid for this, although KC is 0.4 bending, and it's for long-term loading. So when those conditions are not met, you have to adapt this table. And you adapt this table by multiplying the maximum diameters in the table with a factor given by this for bending and a factor given by this for tension. Now, let's assume that we have done that and we have multiplied the table, the diameters in the table with this factor, and now we are going to make an interpolation for the diameter that we use in the reinforcement, and we have to look up what is the maximum allowable steel stress. So we'll make an interpolation in the new table. That means the new table with the alpha phi. Alpha phi. This is the first stress, the second stress, and this is the calculated stress. If we rearrange it, then we can rearrange it like this. But now we see that this is exactly the same as an interpolation, sigma 1, sigma 2, phi 1, phi 2. It's the same formulation as an interpolation in the original table, but with a diameter divided by alpha e, divided by this factor. So what we do is instead of recalculating the whole table, we just assume a diameter phi divided by the factor, and with this new diameter we make the interpolation to find what is the maximum allowable stress. Now let's look at crack width. If you have a tension rod, and this is the cross section with just one bar in the middle, and we start pulling on this rod gradually, then at one point there will be some cracks that are produced. Pretty large cracks with a large distance between the cracks. If we take the same type of rod and we put 4 rebars in each corner with the same surface as the one bar, so the reinforcement stays the same, then you will see that for the same force N, the cracks are distributed over the total length of the rod and are much smaller because they are distributed. So this means that at an increasing reinforcement, the maximum crack spacing and crack width gets smaller. The reinforcement is needed to spread out the total crack width. So now let's look at the definition for strain. Delta L equals L times delta epsilon. That's in fact just the definition of strain. Delta epsilon is delta L over L. And we assume that delta epsilon is the difference in the strain between the steel and the concrete, the mean strain in the steel and the concrete. So that's the delta epsilon. And the L is the maximum crack spacing. It's their max, the maximum crack spacing. And delta L equals the crack width. So if we put it in this general formula, we have our formula for crack width calculation, which is the characteristic value of the maximum allowable crack width equals the maximum crack spacing times the difference in strain between steel and concrete. The difference in strain is of course equal to the difference in stresses, and there is a lower limit to it, which is 0.6 times sigma s divided by ES. Now consider a section in pure tension, not cracked. Then the total force on that section, it's the force in the steel, plus the force in the concrete. It's just a tension rod. I'm considering here a tension rod in pure tension. And the tension force in the steel is the steel stress times the area, and the tensile force in the concrete is the stress in the concrete times the section of the concrete. It means that at the limit, when the tensile force equals the cracking tensile force, it means that sigma s is then equal to FCT, but because it's sigma s, because of a plane before loading is also a plane after loading, then we can change sigma s in alpha sigma c the concrete stress. So we got alpha FCT times AS, and sigma c is of course FCT, the tensile stress in the concrete. Now assume the reinforcement ratio as AS divided by AC, and then we got this formula like it's stated here. Now this is for the cracked section. Now suppose it's cracked just after cracking. Just after cracking, the contribution of the concrete is 0, so the cracking tensile force equals the tension in the steel after cracking multiplied by the surface of the area, the cross section of the reinforcement. Sigma SR is the stress in steel just before cracking. Now, just before and just after cracking, we can make them equal. And by doing so, we see that the stress in the steel just before cracking is the tensile stress in the concrete times a factor depending on the reinforcement. So remember this formula, we will need it just now. SR max is the maximum crack spacing. SR max is experimentally given by this formula. It is important to see that there is a huge contribution of the concrete cover. The more concrete cover, the more the maximum crack spacing, the larger the crack width. And it's also proportional to the diameter. So the bigger the bar diameter, the bigger the crack width. And it's also proportional to 1 over rho, which means that the more reinforcements you put into the section, the less the maximum crack spacing will be. Now, if the bar spacing is less than this amount, then this formula is valid. If the spacing of the rebars is more than 5 times the cover plus the diameter divided by 2, in this case, SR max is given by this formula. In most cases, it means that this is valid for beams, and in most cases, this is valid for slabs. But it's this that is governing the rule, not beam of slabs. And S is the center to center distance of the rebars, that is S, center to center, and you will see that you can easily calculate the S. So we have seen that the characteristic crack width is given by this formula. The maximum crack spacing is SR max. Delta epsilon is the difference between the mean steel strain and the mean concrete strain. Delta epsilon is given by this formula, remember this, that's sigma SR times the coefficient. This is sigma SR, this is sigma S, so that's the delta epsilon. This factor is for 0.6 for short term and 0.4 for long term loading. FCTF we've seen is 0.3 FCK to the power 2/3 for concrete grade smaller than 50. Alpha is ES divided by ECM. And rho effective is AS divided by AC effective. And now AC effective is the smallest of the width times h minus x divided by 3, the width times h divided by 2, and the width times 2.5 h minus d. Then SR max is given by this empirical formula. The diameter, when you use in the same section different diameter sizes, then you should take an equivalent diameter, which is given by this approach. K1 for high bond is 0.8, for plain bars is 1.6. K2, it's given by this formula when epsilon 1 is the biggest stress strain, or the biggest strain in tension. For instance, for pure bending it's 0.5, and for pure tension it is 1. K3 is a fixed coefficient 3.4, and K4 is 0.425. And C is the concrete cover, but it's not the actual cover. It's in fact the minimum desired concrete cover C nom. So C must always be bigger or equal to C nominal. And in the formula for crack width calculation, we take C nominal. Or you can take the real concrete cover, which is there at the moment of the calculation, and then you can change the maximum allowable crack width proportional to the effective concrete cover divided by the nominal concrete cover that is required. A little explanation about the factor K2. It is epsilon 1 plus epsilon 2 divided by 2 times epsilon 1, and epsilon 1 is the greater and epsilon 2 is the lesser tensile strain in the boundaries of the section considered assessed on the basis of a cracked section. So it is this value and this value. If the concrete is in compression, epsilon 2 is 0 because it's the tensile strain. So if you give an example for pure bending, then we got this line here. For pure bending, epsilon 2 is 0 and epsilon 1 is there. So if we use this formula, you will see K2 equals 0.5. And for pure tension, then epsilon 1 and epsilon 2 are equal. And if you fill it in this formula, you find K2 is 1. Crack width calculation is not valid when the concrete is not cracked. Don't forget that. Every time you do a crack width calculation, you must check that the bending moment, the applied bending moment, is bigger than the cracking bending moment. Otherwise, all formulations are wrong. Concrete is cracked when the tensile stress exceeds or supersedes FCTM. This is by definition. Cracking moment is equal to the bending moment that causes a tensile stress of FCTM in the concrete. Crack widths are calculated in SLSQ. Now let's calculate a cracking moment. How do we do that? For a rectangular cross section and double reinforced, we consider a non-cracked section. A non-cracked section means that we take the tensile stress of the concrete into account. It's not cracked, the section. So the tensile stress here we take into account. These are the stresses and these are the corresponding forces. It's the compressive force in concrete and steel, and this is the tensile force in concrete and steel. We use Bernoulli. It means that similar triangles we can express epsilon CT. Epsilon CT is the one here at the bottom. And epsilon S1 and epsilon S2, we can express them in function of epsilon C at the top. We have alpha and we have the elastic behavior of the reinforcement. Now, if we take a transversal equilibrium, then we see that the total tensile force must be equal to the total compressive force. And we will express all items in function of the concrete strain. So NS1 is then equal to this. NS2 is equal to that. It is just simple. The area of reinforcement times the stress in the reinforcement, and the stress in the reinforcement is alpha is ES times sigma S. And sigma S, we derive it from the similar triangles, and ES is alpha EC. So we do the same for NS2. And then the total compressive force in the concrete is just the triangle and multiplied by sigma C. And it's the same for the tensile force in the concrete. Now, if we take this equation and use all those expressions and we solve it for x, then you will see that the depth of the neutral axis of the non-cracked section is given by this formula. We see immediately if there is no reinforcement, the depth of the neutral axis is h/2, which is pure elastic. Remember, the depth of the neutral axis in ULS is 0, is not existing when there is no reinforcement. So this is the big difference. Then FCTM is then the cracking moment divided by the W. W is y/v, is the moment of inertia divided by v, and v is equal to h minus x. Because we are talking here about FCTM, so it's the lower fiber, the fiber at the bottom of the section, and then v is h minus x. So it's there. We are checking this. It's a tensile stress here at the bottom of the section. This is x, and this is h minus x. We calculate the moment of inertia with the definition of fictive sections. And with this formulation, you can easily calculate the cracking bending moment. Now, to save some time and to have some quick identification, commonly we neglect the contribution of the reinforcement and we say AS1 and AS2 is 0. If you do that, then x is h/2 and the moment of inertia is bh to the power 3 divided by 12. Then you see immediately that the cracking moment can be approximated by FCTM bh squared divided by 6. But in fact, it should be calculated taking into account the reinforcement of the section. The maximum allowable crack width under quasi-permanent load combinations for reinforced members is 0.3 millimeters for all environmental classes. In Belgium, we work with environmental classes. Elsewhere, Eurocode 2 talks about exposure classes. So 0.3 is valid for almost all environmental classes. Only when it is inside a building in E1 or in exposure class X0 and XE1, we can allow 0.4 millimeters as maximum crack width. For pre-stressed members, there is a checking of the decompression zone, or it's 0.2 millimeters elsewhere, under the frequent load combinations, not the quasi-permanent load. You can now estimate the crack width and minimum reinforcement of a concrete cross-section. And remember, increasing the concrete quality has a negative effect on the needed minimum reinforcement. See you at next lecture.